So today, I plan to talk a little bit about these topics. I'm going to give a brief introduction to the advantages and disadvantages of VME architecture, and then we're going to talk about key considerations when migrating to PCI Express, server architecture, and VPX. Among the topics of discussion will be the advantages of the PCI Express server, disadvantages, the complexity of the architecture, performance, and cost. And we'll do that analysis for both PCI Express and VPX. At the end, we'll summarize where we're at and what the key factors are. And then we'll have some short discussion on Acromag solutions for both VME, VPX, and PCI Express. And then we'll take questions. VME architecture has been around for more than 30 plus years. It's very well known. It's an industrial primarily with some rugged conduction cooled, and the boards, backplanes, power supplies all follow VITA standards. So this makes it very good for plug and play, which means that you could use various suppliers, various chassis, and integrate systems with a variety of different suppliers and different types of boards fairly easily. Front or rear I/O was predominantly what was available for interfacing to these chassis. You could typically go from as little as 1 slot to up to 21 slots. Typically, a VME chassis has about 20 slots at the maximum, so it conveniently fits into a 19-inch rack mount. VME started with a 32-bit, 3-row, 96-pin connector and migrated to a 5-row, 160-pin connector. Over the years, we introduced VME 64, VME 64X, and 2E SST technologies. A little later, a P0 connector was added to enhance performance with what they call VXS. Over the years, I/O was introduced with industry pack modules, PMC modules, and XMC modules. And processors range from the very, very old 68,000 up to today's Xeon processors. Disadvantages of VME were that processor boards, backplanes, power supplies, they all were much more expensive than, let's say, your old ISOBUS and PCI, and even some of the compact PCI solutions. The other key item was that the VME bus interface chip dictated performance and drivers for your processor boards and other I/O boards were required to be written around whatever VME bus interface chip was used. There were mechanical limitations. Oftentimes when inserting boards, there would be bent pins on the connectors, and it could become very costly to replace a connector on a backplane. Oftentimes when you were communicating with adjacent boards, the bend radius of various cables became an issue, and then heat was always an issue. So one of the things that we were looking at from a performance standpoint, 40 megabytes per second up to 300 plus megabytes per second was kind of the limitation for VME. As I mentioned, the systems packaging solutions, in order to make sure that you didn't burn out the boards or throttle them back, oftentimes you added monitoring of the fans and voltages and temperatures in the system, which added cost. And then oftentimes customers wanted a shorter mean time to repair, so that meant they added pluggable fan trays and pluggable power supply trays, which also customized the VME a little bit and made it a little more expensive. So this is a list of some of the key considerations that I would say your team should consider when moving either to a PCI Express server architecture or moving to a VPX architecture, whether it's Open VPX, which is today's standard, or the older VPX architecture. Operating environment, that is a key consideration. One must understand where this system is going to be required from a temperature range, from a shock and vibration standpoint, humidity. It's key to understand the operating environment and how a lab unit and a deployed unit, if they're going to be sharing the same environment, or what your type of cooling is going to be required. Performance. There are a variety of different single processor, multi-core, or multi-processor, multi-core solutions in the marketplace. So one must know what the performance is going to have to be from a processing, from an I/O standpoint. There's a variety of analog to digital, digital to analog. Some are very high speed on the gigasample per second. Some are very low speed, 500 kilohertz per second. So understanding what your analog ins, analogs out, your digital, do you need 10 gig Ethernet? Do you need 40 gig Ethernet? All these types of I/O requirements will help dictate which is a better performing architecture to migrate to. Another key item is, are you going to be using commercial off-the-shelf or COTS boards in majority of your application, or will it be a mixture of some custom boards, or are you going full custom boards? Software, oftentimes customers would like to reuse existing software from VME when they migrate to PCI Express server or VPX architecture. In most cases, that's very difficult. However, some of the I/O makes it easier to be able to do that. And Windows on VME is pretty similar to Windows on PCI Express server or VPX. So new development, most software for moving over to these new architectures will require some level of new development. And another key consideration is whether you'll require a real-time operating system. And typically, this will be very specific to the processor that you choose and what you're trying to achieve in the application. Mechanically, cabling, sometimes it's almost impossible to use existing cabling in the VME environment and trying to move to PCI Express server or the VPX. However, oftentimes you can make some type of boards that will concentrate I/O, and you will be able to use some of the existing cabling. Swap size, weight, and power. This is another key factor. Oftentimes, an old VME system was used in a certain space or constraint on an aircraft or within a vehicle. So it may be more advantageous to use a VPX system to meet those swap requirements as opposed to a PCI Express server. Time to market is always critical, and your budget. Oftentimes, in a VPX system, there's a much higher non-recurring fee, and typically how much you're going to pay per system will be determined by what your board sets are and what your application and environment. So these key considerations are not all-inclusive, but these are the top 6 considerations that I would take a look at and make sure that your team understands before moving to either PCI Express server or VPX architecture. Some of the advantages of the PCI Express architecture is that it's fairly simple and that you have many server options available, not only commercial, but you also have a variety of rugged server options available from a number of companies. Boards are typically plug and play, and you can also find a variety of lower cost I/O boards, memory boards, and be able to build a system that's significantly less cost than, say, a typical VME or a VPX system. Another advantage is flexibility. There's many processors available, many different sizes of memory, and a lot of different packaging options available. PCI Express form factor, there's a variety of I/O, there's a variety of graphics processor units and FPGA boards in that form factor with various levels of performance. There are also a number of carrier boards that are available to host PMC and XMC cards. These expansion cards come in a variety of performances from low-end serial to very high-end FPGA and graphics processing units. And the carrier boards there are available to take advantage of to integrate into a PCI Express server. Typically, you're going to get much better performance than VME, and in many cases, very similar to performance to VPX. There are multi-core processors, and we're talking about PCI Express interfaces that are very fast. First and second generation are pretty prevalent, but there are many third and fourth generation type solutions out there that offer by 4, by 8, and by 16 lane PCI Express cards. Disadvantages. Most PCI Express motherboards are made offshore. However, you may be able to find companies that take these offshore motherboards and make them more rugged and enhance them for extended temperatures and rugged applications. There are very limited conduction-cooled solutions. High slot count PCI Express servers are much harder to find. With a 20-slot VME chassis, if you were to convert that over to a 20-slot PCI Express chassis, you may find that you have many less options and the chassis would be significantly more expensive. Also, there's some limited cabling options for PCI Express solutions, mostly front I/O and a few board-to-board and adjacent slot capability for connecting I/O. PCI Express server complexity, it's much less complex than VPX. A couple of the things that need to be looked at and managed are, on your motherboard, you have only so many what we call PCI Express connections lanes. So you need to manage how many slots in your chassis, what type of boards you're going to be using, and what type of interfaces they have on them. For example, many carrier boards are a by 4 interface, which means they have 4 differential transmitters and receivers on each. And Gen 1 was rated at 2.5 gigabits per second, Gen 2 at 5 gigabits per second, and Gen 3 speeds at 8 gigabits per second. So when you look at a GPU card or an FPGA card and you have a by 8 interface running at Gen 3, you have a lot of bandwidth in that single slot. Most oftentimes, your motherboard might have 32 interfaces on it, so you might have to break that up into 8 by 4 or some amount of by 8s, 1 by 16. So there is some management there to understand how many PCI Express lanes you have and how you're going to partition that. Going from 6U VME correlates very well to a PCI Express by floor slot. For example, there were 4 industry pack modules on a 6U carrier, and today that's equivalent to hosting 4 Acromag modules on a PCI Express carrier. On a 6U VME carrier, you could host 1 or 2 XMC cards, and you can still host 1 or 2 XMC cards on a PCI Express carrier. The carriers for PCI Express come in half length, 3/4 length, and full length. And there are a very good correlation from 6U VME to PCI Express by 4 slots. The plug-and-play aspect of PCI Express server architecture is what they call enumeration. At power-up, the host CPU detects the devices that are connected, and it defines how much memory space the device needs. What this does is it allows the host CPU to communicate to the correct PCI Express board in the system. So a typical system may have 4 to 8 to 12 different PCI Express cards, and some of these cards may be very similar to each other. So when each card is assigned an address, and when it powers up, then the memory space is assigned for that card. So it's a very nice plug-and-play architecture. PCI Express performance is significantly faster than VME, primarily due to it being a server architecture, also with much higher end multiprocessors, a lot more RAM, a lot more storage capability. Performance is slightly less than VPX due to the ability to customize backplanes in VPX and different architectures like data and expansion plane capabilities. And I'll get into that in a little more detail when I'm talking about VPX. Also, there's less options for rugged conduction-cooled environments for the PCI Express servers. You get into some shock and vibration issues and extended temperature and cooling issues with PCI Express servers. However, there are a variety of 40 gig and 100 gig interfaces available for PCI Express. The cost of PCI Express server architecture is typically, from a system packaging standpoint, lower than VME and significantly lower than VPX. Payload cards are very similar in price to VME, but significantly less than VPX, and we'll talk about why that is. So in general, system costs should be less than or equal to VME and much less than VPX. Also, there is less hardware engineering required compared to VPX when integrating boards. It's often said that with a PCI Express server, if you can have a good software guy, could integrate a variety of different PCI Express boards into a system, whereas in VPX, it would become much more difficult for that software guy to do it, and will require a mechanical and an electrical engineer. In the PCI Express, also, you have the ability to get to market faster. So there's shorter lead times for system packaging solutions. There's shorter lead times for boards most often. So your development time is faster. Therefore, you can get to market faster. VPX offers the most performance of any solution out there. And with OpenVPX, you can fully customize your solution, taking the best-in-class boards from a variety of different manufacturers. Also, from a system packaging and environmental standpoint, VPX offers air-cooled, liquid cooling, rugged conduction cooling in the form of ATR boxes, which are air transport racks, and other types of custom chassis that allow very high-end performance. 6U VME to 6U VPX, we get more I/O in a single slot with the 6U VPX as compared to 6U VME. So oftentimes you could take a higher slot count 6U VME solution and you could make that a significantly smaller 6U VPX slot solution. And we'll talk about that in a little bit. Disadvantages. Moving to VPX, the learning curve for either Vita 46, which was the original VPX spec, or Vita 65, which is Open VPX, is quite steep. It has the most expensive backplanes, chassis, and power supplies. It has the most complex architecture, a variety of different planes. And we'll get into this a little bit, but there's control planes, expansion planes, data planes, utility planes, management planes. There's slot and module profiles, pipes and switches. There's a very complex understanding of how to work with VPX. And other disadvantages are that 3U VPX and 6U VPX are not compatible. You have less I/O when you migrate from 6U VME to 3U VPX. And in the 3U VPX and 6U VPX world, there's not as many I/O boards available. Typically, you're going to end up using some type of carrier board in an XMC, PMC, or Acromag module to get the I/O that you require in your VPX system. And finally, one of the disadvantages is that it's longer time to market for all the reasons above. In this illustration, there's a comparison here of a very simple VME 64 system as compared to a simple VPX PCI Express based system. On the left-hand side, you can see that there's 3 boards. They're all connected to each other through the VME, which is a parallel bus architecture. On the right-hand side, in a very simple architecture, you can see that there's 3 boards. And the board in slot 1 has an interface, what we call a by-4, which is a fat pipe interface to the board in slot 2, and it also has an interface to the board in slot 3. But for the board in slot 2 to talk to slot 3 would have to go through slot 1. So it gets kind of cumbersome once you start expanding with multiple boards. And talking about complexity, VPX spec is over 500 pages long. So it takes a lot to understand the technology. And when you look at the 3U VPX and 6U VPX, power supplies are not compatible. You look at the pitches on the different 3U boards and 6U boards, and you have 0.8-inch pitch, 0.85, 1-inch pitch. You have what they call READY, which is Rugged Enhanced Design Implementation for 3U VPX. There's so many different options and choices that need to be made. When you go to a backplane complexity, you have all these different fabrics, protocols that you can run on the backplanes. So here's a few examples. The one that's typically used in a lot of applications is the Vita 46.4, which is the PCI Express protocol. But as you can see, you have a gigabit Ethernet, you have 10 gig Ethernet, you have serial rapid I/O. So there are a variety of different backplane protocols that you can run. And you get down to different architectures where you have data plane, control planes, expansion planes, utility planes, and different slot, module, and backplane profiles and switches. All this makes VPX very hard to understand, and it takes quite a bit of learning to understand how to put all these pieces together and put a system together. In this illustration, you can see that there's a 3U VPX backplane on the left and a 6U VPX backplane on the right. A couple of observations from this slide is that P0, P1, and P2 are common for both the 3U and the 6U boards. When you go to the 6U architecture, you're adding 4 additional connectors. So your user I/O goes up quite dramatically. And that's where I had mentioned earlier that in 6U VPX, you can take advantage of a lot more I/O available to the backplane as opposed to 6U VME and 6U and 3U VPX. So each one of these connectors is a multi-gig RT2 type connector with 16 times 7 pins on there. And it becomes very expensive for these connectors. Another couple differences here is that they've added alignment keys to this architecture so that you can put in boards and make sure they're lined up, so you could remove the pin stubbing issues of the old VME technology. They've also keyed the alignment so that you can make sure that if you have multiple boards in a system that are a little bit different, that they're not plugged into the incorrectly to the wrong slot. So this is another nice enhancement to help protect boards from being plugged in incorrectly. VPX performance. One of the great things about the performance of VPX is that it'll handle all extreme environments. And another key factor is it offers the most power per slot. In some instances, you can dissipate over 300 watts per slot. But how to cool that becomes a key difficulty in figuring that out, whether you go with liquid cooling and other types of cooling measures. Size, weight, and power optimization. VPX has been extremely good for swap optimization. And then looking at 6U VPX providing more I/O and processing, a couple of examples with 6U VPX, you could use a processor XMC card and add 4 Acropacks and pretty much get a system in a single slot. Another example could be a processor XMC with one XMC site. For example, a graphics processing unit or a field programmable gateway, and get an extreme amount of processing in one slot. Another example would be taking a 6U processor board and adding a processor XMC. In this case, in theory, you could be running 2 different types of processors, and you could be running 2 different types of operating systems all in one slot. Performance is optimized for the application when it comes to VPX. So you can optimize processor, backplane, payload cards. You can partition the system to handle dedicated functions. The cost of VPX is typically tied up in the connectors. These are the most expensive connectors on the backplane. Therefore, all the processors and the switches and the carrier boards that require the mating connectors, those add cost and are very expensive. The systems packaging is most expensive primarily because you have some open VPX backplanes available, but many applications will customize the backplane. So you'll be looking at non-recurring engineering and then pretty much a high cost per slot for a backplane. The power supplies are very expensive in that there's multiple voltage outputs, typically 5, 12, and minus 12, and 3.3 enclosures. They typically include a lot of metal because of the cooling, and they typically will cost significantly more than any type of PCI Express server or VME enclosure. The engineering expertise required to design a VPX system, whereas earlier I mentioned that a fairly sophisticated software engineer could probably integrate a variety of PCI Express cards into a server. In the VPX world, you're going to need some sophisticated mechanical and electrical engineers to figure out how to take the heat out of the box, how to interface the cards and partition the system. So it becomes a lot more expertise required to do VPX, as well as longest development time and eventually the most expensive system price. In summary, migrating from VME to PCI Express server architecture is the lowest cost option and does provide the fastest time to market. PCI Express, much less complex versus VPX being the most complex. However, to VPX's credit, it offers the best performance options, and it does have a better chance of meeting any type of severe operating environment. The key questions that your team needs to answer is, what is my operating environment in the deployed case? What kind of processing? Is it multi-processing? Is it multi-core? Am I going to need I/O that is high speed, low speed? The key thing is schedule and budget constraints. So when you take all these questions and you can actually answer these questions, you're going to find out which one of these architectures is the best one to migrate towards. Just to give you a few ideas, Acromag is still in the VME business, so we still supply 6U VME processor boards based on a Core i7 and Celeron. We still support industry pack carrier cards for both front I/O and rear I/O applications, and we still supply industry pack I/O cards to the marketplace, analog ins, analog outs, serials, digital ins, and digital outs. We also have our Acropack I/O boards, which each one has a by-one PCI Express interface on it, and we have a variety of analog, digital, serial, and Arctic 7 FPGA. We have a new Zinc UltraScale FPGA version coming out. And in the PCI Express world, we have carrier boards for our Acropack modules, our PMC and XMC cards, and we still support an industry pack carrier card that will host 4 IP modules in a PCI Express environment. And then our I/O cards for PMC and XMC include Xilinx-based FPGA solutions, 1 gig and 10 gig NIC interface cards, and a variety of analog ins, analog outs, digitals, and serial and combination cards. On the VPX side, we have a 3U VPX processor and a 6U VPX processor, both based on the Xeon Skylake. We have an XMC Acropack carrier card that allows you to host 2 of our Acropack I/Os in either the front or the rear I/O position. And then we have a handful of 6U VPX carrier cards to host our Acropacks and XMC cards. And we also have a card that does Vita 67.3 called the VPX 4830. And then we have the 3U VPX carrier cards for both PMC and XMC. VPX 4812 can also be used as a switch in a low slot count VPX system. So I appreciate your time and interest in Acromag and in migrating from VME to VPX or PCI Express, and I will be ready for questions. Thank you very much.